2 discusses using lines and linear equations to make models of data. So moving on to slide 2, which we talked a little bit about. Remember, the root of equation is the x-intercept. So if we had the equation y equals mx plus b, and we needed to find out what its root was, we know that the root is the x-intercept. And in order to solve for your x-intercept, you substitute 0 in for y and solve for x. So we have 0 is equal to mx plus b. We're trying to get x by itself. We have to undo any addition or subtraction first. So we have negative b is equal to mx. X is still not by itself, it's being multiplied by m. So we divide both sides by m. And we find out that the root of this equation, which is the same as its x-intercept, is x is equal to negative b over m. It's just another way to find, it's finding the x-intercept, but here we're doing it as a literal equation. So if you ever hear the root of an equation, we're talking about the x-intercept. So similarly, you'll see on slide 2 there, if I asked you to find the root of the equation 2x plus 3 is equal to y, or y equals 2x plus 3, we're going to substitute 0. 2x plus 3 equals 0. We have 2x is equal to negative 3. Divide both sides by 2, and we find that the root, or the x-intercept, of this equation is negative 3 over 2. Right. Moving on to the next slide, we talk about data models, which is a linear graph or a model that describes an authentic situation. Looking at the graph on slide 3, we see that there's a scattergram of points, and there's a line that goes through approximately like half the points. So half the points are above the line, half the points are below the line. We can see it approximately models what's happening with those scattergrams, right? We can see that in that graph, it seems that there's an upward increasing trend, right? That as your x value increases, your y value is also increasing. So we call that a scattergram. On page 4, definition, a model is a mathematical description of authentic situation, and a function describes a relationship between variables. We'll talk a little bit more about functions, just so you can review. Right? So an equation, y equals 4x plus 6. It's an equation. We've got our input and our output. Another way of writing this relationship between inputs and outputs is we can say f of x is equal to 4x plus 6. So this is just giving the function a name. I mean, there's no reason why I couldn't have said g of x is equal to 4x plus 6. And the reason that we want to move to function notation, one, is it's a lot shorter to write. Instead of find y equals mx plus b, find the value when x is equal to 3, versus just f of 3. But also, we're going to start to combine multiple equations and multiple models on one graph. So we want to have a way to name them. Right? So for instance, if we had a coordinate plane with our x and y's, and we had a graph here, and we had something that was decreasing, and maybe we had a parabola. Right? With all of these graphs together, if I said, well, this is the graph of y, oh, this is the graph of y, and this is the graph of y, it's really hard to keep track. So by using function notation, we can much more efficiently say, oh, well, this is a graph of f of x. This is a graph of g of x. This is a graph of h of x. So it allows us to more clearly see which graph goes with which function. And on the bottom of slide 4, we see a linear model is a linear function that describes an authentic situation. So again, we're going to be really big on describing an authentic situation, what's really happening here. And so you could think of it as a way to prove that we actually do use algebra in everyday life. Slide 5 is talking about kind of the correlation that we were talking about. So it's something that's able to describe relationships between two variables. So the graphs A through F here are definitely, it's describing some relationship between two variables, but it would be much harder to draw an approximately, like to say that they're approximately linear related for graphs B, C, E, and F. Where A and D, we can pretty clearly see you could draw a straight line connecting all those points. And I'll recreate that. If this is graph A, and we have our x and y axis, and you have your points, it's not a huge stretch of the imagination to say, oh, all right, well, here's our scattergram. I can make a linear model that describes that because we can draw a straight line through. Here it's exact, it is on a line. But if we have a scattergram in like such as that we have shown in D, and I'm going to do the best I can to reinterpret that graph. So for what we notice, as our x values are increasing, right, our inputs are increasing, our y values seem to be decreasing, but it's not happening at the same constant rate that we're used to seeing. However, we do see that there is a general trend, and if we drew a line, a straight line through here, that we could say that these are approximately linear related, because it is possible to draw a straight line in the general direction, right? We have a decreasing line that represents what's happening in this graph approximately. It's not exact. And that's what we're going to talk about here is for the next couple of slides and several moments is how do we make our prediction about if they're approximately linear related or not. All right, so adding to this, to the, I don't want to say confusion, but adding to your multiple things, you can also pull out the Chapter 2 handout that I gave you that you downloaded. Just either pull that out or that would be okay to print and just kind of keep it handy because you may be able to fill some stuff in as we go. And feel free at any moment, pause the video, go take your break, do what you need to do, but it is important that we follow through with, like, kind of come through here. All right, so I want to show you now, we're moving to Chapter 7, give you some time to get that handout out. Just referring to Chapter 7, excuse me, Slide 7, you have two tables here where P shows the percentage of 12th graders who have ever used smokeless tobacco at T years since 1990. We want to describe the data in the table below with a graph, then sketch a line that comes close to that. So you see the note on the right hand side where we need to turn the data into points. This is very important because the first table on the left, they give us the year and they give us the percentage. And they tell us the year 1992, 1995, 1998, 2001, 2004, 2007, 2008. But in the question, it said we had T years since 1990. So when we graph this, we don't want to have our graph and say, okay, well, here's 1992, because where do we begin, right? The world didn't start at year 0. We have our BC errors. So when we say T years since 1990, well, that means 1990 is equivalent to T equals 0, because that's when we're starting to collect our data. 1991 is when T is equal to 1, and so forth. So we need to turn those plots where it says year to percent into data points, and that's the second table. So I'm going to erase this, and you have the data on the second table, where here you have year equals 2 because it was 1992. Year equals 5 because we're talking about 1995, 5 years since 1990. 8 because it's 8 years since 1990, etc. All right, I'm going to pull my graphing calculator out and show you how we can do this on the graphing calculator. All right, so pardon the little potential motion sickness as I move the webcam. All right, so it's just your standard graphing calculator. If we need to go in to plot points, we are going to hit second and then stat plot. Nope, just joking. Hold on. Wait. I very rarely use my calculator. All right, so we're going to do second stat, and then this comes up and we put edit, and here we have several values. So if you have numbers here, you can scroll up to L1 and hit clear and enter, and it will clear everything. So I'm going to show you again how we got here. If I can find my quip. All right, so we're on our screen. We're just going to hit the stat button, and we hit enter because edit is up there, and we should have a screen that looks like this. If you do have numbers that are coming down, arrow up to L1, hit clear and enter, and it'll disappear. You can scroll over to the next and do this. Okay. So these L1, we're going to put in our X values that we see in that second table. So I just hit 2, enter. So 2 for 1992, 5 for 1995, 8, 11, 14, 17, 18, right? So make sure you have all of your data points, and then we're just going to arrow over to L2, and I'm going to put the percentages in there. So 32.4, enter, 30.9, enter, 26.2, enter, 19.7, 16.7, 15.1, 15.6. Right, make sure we have it all in there. I'm going to clear my y equals graph. Right, so I'm just going to get rid of what I had in the y, so you maybe check to see if there's anything stored in there. I don't know if they clear everything when you rent your calculators. All right, so our stat plot, again, we went to edit, put our values in, and then we can come up here to the button that says graph. And if you see your blank screen, that's where you go to second stat plot and select where it says plot 1, hit enter, and then turn them on. We want to scroll down to list or type. We want them in a scattergram. So we're going to hit enter, and then we can go back to graph. And find out why they're not plotting. Technical difficulties. Bear with me. I think I gotta change my window setting. Alright, so I apologize for the delay. I'm going to hope that yours is displaying as it should. Let me get this straightened back in here. There's probably some setting that's funky on mine, as I had been using radians and I probably never took it off. I don't know if this will help anything. No, so that's my own investigation that I have to find out what's happening with my calculator. So I apologize. The nice thing is we don't actually need to see the data points, because if we take a look at our slide 8 tells us what we need to do in order to find these. Maybe I do need to graph to zoom in. If we need to change how what we see on the graph, you hit window and you can select how you'd like the window to be shown. So I'm going to change my Y min, and the Y minimum means what's our range? Well, we don't have anybody that we don't have a negative percentage, and I'll change my Y max to 50 because we don't have any. Actually, I'll change it to 35. We don't have any more than 35% of the people 18 and younger smoking. We'll try graphing this. There we go. All right, I had the wrong zoom button. So all I did is I went into window and I changed the dimensions on my screen. So we didn't have any negative x values in the domain, and then I went up to x equals 50, which we could have gone up to x equals 20 because we don't go anywhere past 20 years since 1990. And then I went down to the Y min. We don't have any negative values. And the Y max, I looked to see, well, what's our biggest Y value for the range, and I just picked a larger number. So if we look at the graph, we see that we have the plots that look like this. They're not connected. Then the reason they're not connected is because I went into the second stat plot. When I went to plot 1, hit enter, made sure they were on. But when I went to type, I selected, see how it's blinking on the scattergram portion. If we had selected the other ones, our lines may have been connected. So back to the graph, it's approximately linear related. We see that as time is increasing, the number of, or the percentage is decreasing. But we need to find, to see if we can make a linear model. So looking at the graph, or excuse me, on slide 9, we can draw a line that contains approximately all of those points, and that's seen on slide 8. And notice that I have that slope, the change in y over the change in x. What we really did is we just found what we call linear regression. And linear regression is simply a line that is approximately linearly related to our data values. Go ahead and flip over to slide 10. And we can use our calculator to find this linear regression. Right? So in order to do this, we're going to go back to our stat. We're going to use the right arrow and go over to Calc, and you can arrow down to number 4 where it says lin reg and in parentheses ax plus b. You're going to hit enter. Here you have, it's telling you that you're using the X list L1 and your Y list L2, which is exactly how we had our stats set up. So you could hit enter again. Keep hitting enter. And until you get this, where you have in the form y equals ax plus b, you're found, they say that your a is negative 1.18 and your b is 35.1. Well, notice that the calculator is using y equals ax plus b, but that's, get in there, but y equals ax plus b is in y equals mx plus b form. So if they're tell us that a is equal to negative 1.89, I'll carry it out to the hundredths place, that's telling me that our slope is negative 1.89. The b is our y-intercept. So we can take all of the information contained from our calculator where they just calculated our linear regression, and we can say that the line y equals negative 1.89x plus 35.11 is the line that is approximately linearly related to the model. So we took an authentic situation where they had done studies about the percentage of young people who smoked since 2 years since 1999. We plotted the points. We saw that there was a general trend, and then we were able to come up with a line that was approximately linearly related. Go ahead and take a look at slide 11. So we'll talk about doing this in several different ways. So here we're told that n is the average number of times a person visits the library per year. And we know that the variables a, the age, and n, the number of times, are approximately linear related. Let me get the screen back. Technology is wonderful, but making sure you can see everything. And again, I really appreciate your patience for these, like this virtual lecture. So we know A is the age of the person, and N is the number of times they visit the library. And we're told that they are approximately linear related. Okay, and I'm just pulling this information from slide 11. So the average number of times that a 29-year-old, right, that's their A, visits the library per year is 11. That's the N. So we could have it set up as our, 29 is equal to A, L is equal to N. But then we're told that the average number of times a 59-year-old visits the library is 9 times. So we look like we're starting to develop input-output tables. Right? So their age determines the number of times they visit the library. So a 29-year-old visits 11 times. A 59-year-old visits 9 times. There doesn't seem to be a huge difference there. But if we need to find out what what model will use this to approximate the linear regression, or what mathematical model could we use to show this? Well, right now we have 2 points, right? This is x1, y1. This is x2, y2. So we just don't have the points in the middle. We can find the slope of the line, or the equation of the line after we find the slope. So we have our y equals mx plus b. We need to calculate our slope, which is simply our y, y1 11 minus y2 9 divided by x1 minus 59. Right? And we see that the number of adults drop as the age increases, so we expect a negative slope. So 11 minus 9 is 2. 29 minus 59 is negative 30. You have common factors of 2 and negative 30, so we can say the slope of this line is negative 1/15. Right? So I'm going to plug that information in up here. Negative 1/15. I'm also going to dispose of this marker. So what's left is we need to find our b. In order to do that, we just pick one point. So I'm going to pick, it doesn't matter, and you can see it with yours. I'm going to pick the point 59, 9. So when I pick the point 59, 9, we're going to use that and substitute everything that we know into our equation. Well, the y value is 9. We calculated the slope. I'll say the slope is equal to that negative 1/15, negative 1/15. And we need to use our x value, which is 59. And we have our plus b. So we used all of the information we have from y equals mx plus b. We calculated this slope. We picked one data point and we put it in. So now it's time to use our calculator. So second quit to get back to a calculation screen. I'm going to say negative 1 divided by 15 equals times 59. We have negative 3.93. I'm going to assume it doesn't come nicely into it does. Negative 59/15. So we have, and you can use it as a decimal if you'd like. You can use it as a fraction. It doesn't matter. I tend to enjoy fractions just because of the math that I do elsewhere. I know that leaving it in fractions is sometimes the easiest thing to do. So we have 9 is equal to negative 59/15 plus b. Well, we notice we're trying to get b isolated by itself. Right now it's not. So we need to subtract this from 9. We're going to say 9 minus, and I'll show you what I'm going to do here. I'm going to say go up to the second button, second answer. That way I don't have to type this back in. I hit enter and we're left with 194/15. So b is equal to 194/15. Again, when I did that, I just did 9 second answer and hit enter. So it used the number that was right in front of it. So it helps us not have to type anything in. So we know that this was our m. Our b is 194/15. I have very limited room on my whiteboard. I'm thankful for it. So when we come back, we plug it into our equation. Y is equal to, we know the slope is negative 1/15. We have to put our input in there, x, and we have our b, which is positive 194/15. So this linear equation models a fact that when people are 59 years old, they visit the library on average 9 times, and 29-year-olds visit the library on average of 11 times. We notice it's decreasing, so we should have a negative slope, and that is exactly what we have. Great. I want to move over now to that handout for Chapter 2 so we can kind of work through and practice with some of these. So pardon me while I get myself situated, reestablish map. All right, so this is review that I would ask you to complete, right? For here are your values, determine if they are linear. Remember, to do that, we look at our change in y values over our change in x values, and they have to be constant. Here, this is a little bit of kind of guess and test, but trying to decide they are linear models, so you determine what the slope is given the information here, and it is a little bit more challenging, but use your critical thinking skills. I know you can do it. Right? So something to do after this. Now, another example to practice what we just talked about. We're told that n is the number of robberies per 100 branches at T years since 1995. We want to find the following data with a graph. So the first thing we need to do is we're saying that year 1995 was really equal to T equals 0. So we need to find what our x values are in terms of T years since 1995. So 1997 was 2 years since 1995. 1999 was 4 years. So go ahead and work at finishing this as far as all the way down how many years since 1995. So as long as I did my math correctly, which we never know in my current state, 2 years, 4 years, 6 years, 8 years, 10 years, 12 years, 14 years, 16 years, 18 years, right? So those are our x values. We could do this by hand, but why bother? We're going to come back to our calculator. Go to second. Nope, I don't need second. We're going to go to the stat, edit. We still have our points in here, so I'm going to arrow up to line 2, hit clear, and hit enter. Everything goes. I'm going to do the same to line 1, hit clear, hit enter. Everything goes. And now we just need to put these points in. So I'm going to just go down my x values. So 2 years since, 4 years since, 6 years since, 8, 10, 12, 14, 16, 18. And you can do each point at a time. For me, it's just faster to go right and over. Now I'm going to arrow over to line 2, and I'm going to start putting my y values in. So 10.6, enter, 8.8, 10.3, 8.7, 7.7, 6.0, 6.0, 5.3, 4.5. All right, make sure that we have the same number of x values and the same number of y values. We do. I'm going to go over to my zoom button, and I'm going to go down to zoom. We should have zoom fit. Right? So zoom fit. And here is our new data. So what we see is happening is that time is going on. The number of bank robberies is decreasing. And then we can say that it's approximately linearly related because it looks like that we could draw a line. I need something flatter that we could draw a line through those data points where we have approximately half the data on the left and half the data on the right. So if we want to come up with an equation for that line, this is where we're going to go back to Stat, arrow over to Calc, down to Linear Regression, hit Enter. This is just going to confirm that we have our values where we want them to be. Keep hitting Enter, calculate, and we find that the linear regression model, we have a slope of negative 385, 385 thousandths, and a y-intercept of b 11.394. So if you're asked to plot the points, you'd want to plot points that look like this. Everything would be graphed. If you're asked to find, which we are, you'd sketch a line that comes close to the points, and we did. Right? I'm okay with that. I'm not going to make you hand draw a scattergram. I know Mariah said that you're not a big fan of scattergrams, so you're welcome. If we need to take this and put it into our linear regression, right, I didn't write it down, so I have to go back to my stats, go over to Calc, linear regression, enter, enter, enter. We're told that A is equal to negative 385 thousandths and our B, so we can write our approximately linear related equation to be y is equal to the slope that they gave us, which is negative 0.385x plus 11.39. And this is our equation. Our slope is negative 0.385. Our b is equal to 11.39. Done. So a lot easier than having to graph this by hand. Go back to slide 12 for me, if you would. All right, slide 12 says model breakdown happens when a prediction is false. Right, so we can draw something that says we're approximately linear related, but something weird could happen. So if we look at the graph that's on slide 12, and we look at the data that's there with it, get this to look not so wonky for you. A 4-year-old child is 39 inches tall. It's expected that he will grow at a rate of 2.5 inches per year. So if he is 5, then he is going to be 39 plus 2.5 inches. So he'll be at 41.5. If he is 6, I'm having technical difficulties. I hope you can still hear me. I think I hit the mute button. I'm going to pause the video and come back and test it. All right, thank you. I'm hoping you can hear me now. I apologize for that. All right, so then if he's at 6, well, then he's going to be 44 inches. All right, not bad. So here's our, he's 0, he's 1, he's 2, he's 3, he's 4. So at 4, we'll say he's 39 inches. At 5, he's 41.5 inches. At 6, he's 44 inches. So right, we have a slope here of 2.5 inches because that's the rate that he's growing at, right? Every year he increases his height 2.5 inches. It's very much linearly related. But if we needed to say, well, how tall is he going to be at age 50? Right? We draw our line, age 50 is going to be way out here. Is there any way that he's going to be, like, we have our slope of our equation. If we needed to find this, right, we could do it. We're given our y equals mx plus b. We know it's approximately linear related. Our slope is given to us as 2.5 inches per year. So we can substitute in any of our points. So I'll say 39 is equal to the slope 2.5 times 4 plus some y-intercept, right? So I just use this data point, substitute it in. So we have 2.5 times 4. 10 is equal to 39 plus b. 29 is equal to b. So our equation is y is equal to 2.5x plus 29. Meaning that when this child was 0, he was 29 inches, which seems a bit long, but maybe not. Maybe he was gigundo. So if we wanted to predict how tall he's going to be at age 50, that's our input because his height depends on his age. So we'll say y is equal to 2.5 times the age 50 plus 29. 2.5 times 50 plus 29. Well, this says that he will be 154 inches tall. To put that into context, I'm going to divide by 12, and this says that he is going to be 12.8 feet tall at age 50. So, unless this person is in the Guinness Book of World Records or there's some oddity, we're not going to have a 12.8 foot tall person. So what happened? Well, what happened is what we call model breakdown. Model breakdown happens when we can find a model that makes a good prediction, but only for a certain set of values. I'm looking through the next slide where I want to go to. But obviously, like, we have model breakdown that occurs here. Because, up until the person gets to maybe 6 feet tall, whatever that comes up to, it may be a good approximate linear relation, but we know that growth slows down. So we know that we have model breakdown when a model is not really predicting the authentic situation. So I do want you to use and put definitions in for model and for linear model given the information that we've used. And then I also want you to think about what happens with model breakdown with the bank robbery equations. Interpolation has happened when we are talking about model breakdown within the data, and extrapolation is what we talk about model breakdown outside of the data. So I would like you to please make sure that you read section 2.1 for more information on that, and we'll talk about it more when I come back in. Also, heading back to the slides, I have several opportunities in here for you to see what's happened. Right? So for you to go through, and on slide 13 we've got the percentage of people smoking since year 1970 up to 2015, and go through the slides, show you how to plot those points, what you're going to see, and noticing how the points on the line can be can be used in the model. They don't have to be. I'm going to see if I printed out this slide. Here, I got to readjust this. Okay. So this is slide 13. So again, we're talking about P being the number of people or the percentage of people who have smoked since year 1900. So when we look at our data values, for our X values, we know that we have to go from 1900. So 1970 is 70 years since 1900. We've got 80 years, 90 years, 100 years, 105 years. So these are your X values, these are your Y values. The 37.4. So you can think of this as L1, you can think of this as L2. Slide 14 walks you through how to put that information in there, reminding you to do your stat plot. If you're not finding the points, like I had difficulty the first time, you can always hit the zoom button and scroll down to zoom fit, and it takes the guess and test out. It will allow you to just the screen gets to what it needs to for zoom fit, right? And your points are there. So slide 14 walks you through taking care of those points. And I want to take a look at slide, where is it? Slide 15 for a moment. Take a look, please, at the slide and look at the data values, right? See if it looks something like what you see on your graph. Just work through your points. Give you a few moments. All right, so when you graph that, hopefully, maybe, potentially, your graph looked something like this. Oh, what we notice on this graph, and it doesn't always happen, we have the data point 7034 actually falls right on our line. And this is this point here, 1970, 37.4. And also 2005, or 100 years, 105 years since 1900, also falls right on the graph. Right? We don't always see that. We don't. But nicely, what this is going to do is it's going to allow us to find our slope here. It's going to allow us to use our slope, or to calculate our slope. So we're going to take the difference in our y values, 37.4, and we're going to subtract 19. So our slope is equal to your change in y over your change in x. So the slope is 18.4 over, now we need to find the change in our x values, 70 minus 105, negative 35. So the slope of our line is negative 18.4 over 35. Next, we need to find our y-intercept. So remember, we have our equation y equals mx plus b. We substitute what we know for a point. So I'm just going to use 70 and 37.4. So our x value is 37.4. Our slope we just calculated as this mess, 18.4 over negative 35. We know our x value is 70. We're left to find our b value. So I'm going to plug this into the calculator. Just going to have in parentheses 18.4 divided by negative 35, close parentheses, multiply by our input of 70. We have negative 36.8. We need to subtract a negative, so what we're really going to do is we're going to add this to 37.4. So here we have 37.4 is equal to negative 36.8 plus b. So this is being subtracted. We want to add it to 37.4. We're going to have 37.4 plus, I'm going to multiply it by negative 1. Second answer, we find that our y-intercept is 74.2. With our y-intercept of being 74.2, our equation is y is equal to our slope, negative 18.4 over 35x plus 74.2. That is how we find a linear model. If you had done linear regression, just out of curiosity, try it using the linear regression and see what happens. You probably get a decimal. Moving on to slide 18. This is one that I would like you to make a note of and try for yourself at home. Well, you are at home. But I would like you to work through it and then email me if you have any questions, or just bring them to class. I mean, I'd prefer to have you email them to me, and I'll do my best to answer while I'm away. The solutions are also there on the graph, so you can work through those and see what happens. You notice slide 22 is going to say that there are a couple of models that will work well for you. And the book also talks about how to pick the best model. And we continue to go down and see what happens about with model breakdown with this cell phone example. So if you were looked at the age grouped, taking the average of the age groups and percentages, look at what happens when we graph that. We say that when somebody is 0 years old, they were sending 106 text messages. And there's a problem with that, right? So this is slide 26. I'm sorry, slide 26. If somebody's 0 years old, they're not sending 26 text messages or 106 text messages. It just doesn't make sense. But we do see that as people get older, after age 20, things start, right? There is an approximate linear relationship that happens here. So according to the model, 106% of newborns use cell phones or receive text messages. Well, one, it's impossible to have 106% of somebody. Right? So we're getting false estimates because we can't have a percentage larger than 100, and newborns don't send or receive texts. That's in lines 27. if we look at slide 28, the A-intercept, which is our X-intercept, it says that when somebody's 71 years old, that 0% of those people send or receive messages. But I don't think that it's true. In fact, I know that up until a couple of days ago, when my second mom passed away, she was 74 and she was using her cell phone every day. So there's some model breakdown that happens here. And this is where I wanted you to read about the interpolation and extrapolation. Interpolation happens when part of the model breaks down between the coordinates of the data, meaning between where the person, like where we had the data between 21 years of age and 60 years of age. So it's happening in between. Extrapolation happens when it's outside of those t-coordinates. So looking at the graph on page 30, we see right in here that blue space that's in there, those were our data points, because it went from 20 years old to just over 50 years old. Right? So that means we can have really good faith in this model because we actually have data points that fall along the lines. That's our interpolation. Anything outside of those data points, so younger than 21 years of age, we have extrapolation, because we're losing faith in that. Right? And you think conceptually, it just doesn't make sense that over 100% of newborns are going to be sending text messages, or even the data point that says 4-year-olds are sending 100, like they're 100% of them are sending or receiving text messages. I know it's more common for toddlers to have access to their parents' phones, but 100% of them seems a little bit steep. And the same goes for after 60 years old. Again, we lose a little bit more faith, and we know that we can never have negative text messages or negative percent. So we have no faith. It becomes our model breakdown. Right? So definitely read some more about this. Age 31 tells us that it gives us more information to prove that why we have model breakdown here, that it's not really giving an authentic situation. So I'd also like to make a note on here that in here with your linear model, I'd like you to kind of in your own words write down what model breakdown is to you. Slide 32 talks about modifying the model, and you can read about that in the text. For our class, I'm not going to be too concerned about that. I just want you to know that we can make efforts to modify a model to try to eliminate or at least reduce some of the model breakdown. So I'm going to stop this video and I'm going to move on to making function notation and prediction. So we can stop this and we'll be right back with 2.3.